Ludwig, sorry, Boltzmann, got to pronounce it right. German. Inman, it's English. Yeah, there you go. So now you guys know the inside joke, and everyone who watches the video is going to be like, what was that? So Boltzmann was the one who kind of came up with a really good definition for entropy as far as the molecular entropy that we're going to be talking about. It was engraved on his tombstone. That's just, so there you go. His life was about chaos, and he wanted it on his tombstone. But basically, he's the one who kind of figured all that out. And if you want to read more about that, it's in the book, and it's actually kind of this new book does a much better job of describing what entropy actually is on the molecular level than the old book did. So it's worth reading, maybe, if you really want to understand what entropy is. You're not going to be tested on any of that stuff, but it's interesting. So that's what I put on the reading guide, is that you don't need to cover that section in your reading guide when you're doing your outline or your notes or whatever. But if you want to read it, it's there, and it helped me. But I teach this stuff, so so entropy on the molecular scale. Basically, like I said in class, you've got to be thinking about probabilities, different possibilities of a molecule being turned a certain way or being in a certain place, those sorts of things. So then we need to talk about how molecules move, because there's some different possibilities for their movements even. So different types of motion they can have. Translational, so that's where the molecule moves from one place to another place, okay? And that's what we probably usually think of when we think of movement. But within a molecule, there can also be vibrational movement, where the bonds actually vibrate, okay? And you can have vibration where they're sort of stretching out from one another. So these two atoms down here, the two hydrogen atoms, are moving away from the oxygen, and then they come back towards it. So that kind of vibrational motion. You can have a vibrational motion where they're actually pushing, the hydrogens are pushing closer together and moving further apart. Or you can have something like this, where one of the hydrogens is getting closer while the other one's getting further away. And then you can also have rotational motion, where it's spinning. So all of these are possibilities for the movement of a water molecule, where it's really not even moving from one place to another. It's just moving, right? And all of that has to do with entropy. Because entropy, again, is just how many possibilities are there for the way that something can be positioned in space. And so all of these are different. I think we're going to get to this in a little while, but do you know what you can do to stop the motion of a molecule completely? Cool it down to absolute zero, right? 0 Kelvin is the coldest possible temperature. And at that point, that's a theoretical point where the motion of molecules completely stops. So guess what the entropy is at 0 Kelvin? 0. Yeah, there is no entropy at that point. Okay. So you want things to be perfectly ordered, just make them 0 Kelvin, and they will be. But then you'll be dead. So, I mean, kind of pointless.
For your real life application.
Right, yeah.
You want things to be completely
Right, so for your real life application. It wouldn't work. Sorry. Unless you could, like enclose everything else, and then you're outside of that enclosure, then maybe you'd be okay. All right, so Boltzmann, he basically thought about these snapshots, right? So the molecules are always moving, but you take snapshots of these molecules, and every snapshot you take is going to be a little different as far as where the particles are and how they're oriented and all that stuff. And if you could just think about that, I mean, it's kind of staggering to think about, really, all of the different snapshots. So basically, entropy is how many possible snapshots are there given a certain enclosed area, and I mean, obviously, that's a number that we can't even comprehend, right? But that's the idea behind entropy. He called this a microstate.
Gordon, can you come to the activities office, please? Gordon, to the activities
I'm going to go over this pretty quickly, actually, because we don't.
3 o'clock, let's make it. 3 o'clock, activities office. Thank you.
Make a meeting right
funny announcement.
3 o'clock.
Which is rather personable for an announcement over the intercom. So anyway, you don't need to know this equation, all right? This is not on the equation sheet. You don't need to know this, but there's another K, just in case you wanted another one, you know, because we don't have enough already. But S is usually the term for entropy, so you do need to know that, okay? But we're going to have other ways of finding entropy, and you don't really need to worry about that particular equation. Here's what you do need to worry about, more of the theoretical, qualitative sort of stuff. So entropy is going to increase with the number of microstates. So, and that's just another way of saying the number of possibilities, right? So the more possibilities there are for where the particles can be, the more entropy you have. So entropy is going to tend to increase with temperature, okay? Temperature may not necessarily affect, if you're at a constant volume, it may not necessarily affect where the particles can be in space, but it might affect their vibrational motion or their rotational motion, those sorts of things. And so you can increase your entropy by increasing temperature. You can increase your entropy by increasing the volume of the container, or if a reaction increases the number of independently moving molecules, okay? So at a reaction where you start out with 2 moles of something and then you end up with 4 moles at the end, that's going to increase the amount of entropy because now you have more moving molecules and so there's more possibilities. And entropy is also going to increase with the freedom of motion of molecules. So, and this is, I think, going to be fairly obvious for you. A solid has much less freedom of motion, right? Because these things are kind of locked into place based on their strong intermolecular forces. So they're kind of stuck where they are, and the only kind of motion that they usually have is vibrational, right? They can't even really rotate or anything. So a solid has a fairly low degree of entropy, right? But a gas is going to have a very high degree, or a high amount of entropy. Because gas molecules are much more free to move wherever they want to move. And then generally when a solid dissolves in a solvent, the entropy increases. And the reason for that is because you have more, you've got this solid, right, very highly structured and arranged. And the water molecules start to pull that stuff apart. And so now you've got free ions kind of floating around in the solution, okay? So there's a greater amount of entropy there, even though you are creating some intermolecular forces there, right, with the water molecules. But it's really going from a solid state to more of a, you know, each individual ion being surrounded by water. So an aqueous state. In general, entropy is going to increase when gases get formed from liquids and solids. Liquids or solutions are formed from solids, or the number of gas molecules increases, or just the number of moles in general increases. Right, so any of those things can increase entropy. And this is, I don't think you're going to have too much difficulty with this at all. It's all fairly conceptual, and it's just looking at something and saying, is there going to be more chaos, more disorder in this system, you know, than there was before? And then you can kind of tell which direction the entropy changes. Now, I think you might have a practice problem in the book about that. Okay, so here's the absolute zero thing that we were talking about. Let me see where we are in the book, because I might want to go over an example just to kind of show you. I don't think you, like I said, I don't think you guys are going to have much difficulty with this at all. Yeah, so there's a sample exercise in the book, which I should have put on here, but basically you have to predict whether the delta S is positive or negative for each of the different processes here. This is on page 814 in the book. So letter A, it has water, H2O liquid, going to H2O gas. And I'm just going to write it on this page. So H2O liquid to H2O gas. So would that be an increase in entropy? Okay. I mean, it's going from a liquid to a gas, so that's fairly obvious, right? So the delta S for this one would be positive, okay? The next process, Ag plus Cl minus, forming AgCl solid. Delta S for that one would probably be... Now, the plus and the minus, I didn't write the state of matter here, but what would this be? These would be aqueous, right? Okay, so they're floating around in solution. They come together and form a solid, which is much more highly structured. So that's a negative entropy change, okay, because we're going towards more order. Now, why can that happen? Because I thought I said yesterday things don't get more ordered, right? Well, it is forming bonds. So, I mean, did I lie to you yesterday that things can get more ordered? What, do you remember what I said? It wasn't necessarily that things can't get more ordered, but what did I say? Sorry, I didn't hear any of that from any of you. Oh, say it again. Say it again. Okay, you have to do something to it. So ultimately, if you compare, if you compare the entropy change here to the entropy change in the universe, overall, the amount of entropy, the disorder increases in the entire universe. All right. So every time something ordered happens, you're just fighting against the universe, right? Okay. So you clean your room, you have increased the entropy in the universe by doing that. Okay. Kind of depressing to think about, you know? Like every time you do something that increases the order in a system, the surroundings increase in disorder by a greater amount than that. Okay, so the entire entropy in the universe has now increased. All right? So you can't win, all right? No matter what you do, you're increasing the entropy in the universe. Or at best, you're keeping it the same, right? But in the system itself, the entropy can decrease. The next one is solid iron plus oxygen gas goes to iron oxide, which is a solid. Can you guys come up with the answer to that one without seeing it written? So you got a solid and a gas going to a solid. It would be negative, right? Okay, so the delta S for that one would be negative. Again, the entropy change is, it's going to have lower entropy at the end than it does at the beginning. And then the last one here, N2 gas plus O2 gas. Well, here, I'll write this one out. N2 gas plus O2 gas yields 2NO gas. Oh. I'm hearing I'm hearing increase and decrease on this one. Yeah, but I mean I could rewrite this as N2 plus O2 yields NO plus NO, right? That's what the 2 really means here. I've got 2 particles on the left side, 2 particles on the right side, and they're both gases. So they're just trying to trick you on this one. It's not that it stays the same necessarily, but it's going to be impossible to predict from what we know. Let me see if it says here. Well, no, not really. I mean, you could maybe look at the molar masses, but I mean, yeah, I'm not sure, given the information that we have, that we can figure it out. And it actually doesn't say in the book. I was looking to say if it said, here's what it actually is, but we can't predict it, but it actually just says we can't predict it. So, so that's that. There's a really interesting entropy and life thing on here as well, in the book on page 815. And it basically says the same thing, this really depressing statement at the end. Each cell exists at the expense of an increase in entropy in the universe. So thanks a lot, cells. Right. So anyway, it's just interesting. I like this stuff. Ah, seriously? I really should look at my notes before I go through this. Okay, so there's the problem we just did. We got another one here. Okay, here we go. Well, that's just more practice, which we're not having too much trouble with this, right? I mean, it makes sense. Yeah. So let's move on.
Yeah.
Predicting which one has the higher entropy. Let's see if you can do this. Choose the sample that has a greater entropy in each pair. 1 mole of NaCl, 1 mole of HCl.
HCl.
Greater entropy, yeah, it's HCl, right? Because it's gas molecules instead of solid molecules. Okay. 2 moles of HCl or 1 mole of HCl. Yeah, the more particles there are, the more possibilities there are, so the more entropy, right? 1 mole of HCl or 1 mole of argon at 298 K. Ooh. That one's kind of tricky, isn't it?
Yeah. What if the argon says that hydrofluoric is too greater mass? Or no,
Well, yeah, see, it's not going to be a mass thing. There is a difference here. Well, yeah, there is that.
Is it like the number of atoms or like the range of motion?
You could talk about range of motion, maybe. They're going to have the same number of atoms / molecules, right? But molecules, remember, can have vibrational motion, right? And rotational motion that makes them different, right? I mean, argon, I guess, can have a little bit of the rotational motion in a sense. The other thing to consider here, and I'm not exactly sure which one of these is more important, or maybe if they even take it into consideration. Well, okay, they're both gases, so the intermolecular force of the thing is going to be negligible. So really, the only thing that we need to look at here is the HCl can vibrate a little bit more, can have those degrees of freedom where the other one doesn't, okay? Capable of storing energy in more ways than the argon. It can rotate and vibrate. The argon atoms cannot. So they're saying they can't really rotate either. Although, I mean, we do talk about these atoms being a little bit polarizable so that you can have more electrons on one side than the other. So there might be a little bit of, like, if you rotate it, maybe it's a little different on one side than another, but it's not going to do anything as far as vibrational. Okay. So that's that. Standard entropies. This is going to be a lot like the delta H of formation. All right. Basically, standard entropy, because we can get down to 0 for the entropy, we don't just have to talk about delta H's, we can actually talk about just S. Okay. It's kind of an absolute number. Since we know that if you get something down to 0 Kelvin, it will have 0 entropy, you can kind of work from there and figure out an absolute value for entropy. Okay. Standard entropies tend to increase with increasing molar mass. So, in general, the bigger they are, or the more massive they are, I guess I should say, the more entropy that they have. And that's mainly because then you've got more moving parts, right? So the bigger the mass, the more protons, the more electrons. A lot of times, the more atoms you're talking about in the molecule. So then you've got more entropy. Larger, more complex molecules have greater entropies, and again, that's fairly obvious because there's more ways that this can do vibrational motion over here than just methane over on the left side. And basically, this is going to be just like your delta H of formation, which is why it was good that we talked about that today in class. You just take products minus reactants, and you can figure out the overall delta S for a reaction just like you can with the delta H. Okay. And then you have to do the same thing with your delta S's. You multiply the... Actually, I think this equation was written wrong. It's not a delta S here. I don't think. Let me double check that. But I think it's just S. Yep, it is. So there's no change there. It's just the absolute.
At 2:50. Thank you.
Okay.
Thank you for calling Holt High School. Our main office is open from 7 a.m. to 3:30 p.m.
Oh my goodness. I'm having some real intercom issues during this video today.
Please enter it now. To use our employee directory, press the county. For attendance, press 1. For
Sorry.
activities, press 2. For guidance, press 3.
When are they going to figure out what's going on and stop it?
For nurse, press 5. For all principals, press 6. For library, press 7.
That should be
For
fine. Yeah.
cafeteria, press 8. Or for the main office, press 0. Thank you.
You're welcome. Okay. All right. Anyway. So yeah, they didn't. They just, I guess they decided to let it run its course. I don't know. Yeah, they were just making an announcement, so I don't know. All right. So to find your delta S, you take the S of the products minus the S of the reactants. Okay. So there's no delta in that part. So here's an example. I actually really like these notes now. They have the examples. Delta S for the synthesis of ammonia. You would have to look up the S values in your book. Now, if you have a question like this on the test, I'm going to give you the S values, or the AP exam would give you the S values. But basically, if you have the S values for this, you can kind of figure this out. Whatever the S value is, the entropy value is for NH3, we'd have to multiply that by 2, right? And then we would subtract the entropy for N2 plus the entropy for H2, whatever that is, times 3. Now, N2 and H2, when we were doing delta H of formation, do you remember that those are 0? There's the bell. Do you remember that the heat of formation for any element in its kind of natural state is just 0? It's kind of how we defined it, right? It's not that way with entropy, okay? All of these things have entropy because they're not at, the standard S0. That 0 means it's at 25 degrees Celsius. And at 25 degrees Celsius, everything has entropy, right? So these are not going to be 0. They're actually going to be a number. And I just covered this thing. But here's how you would work it out. And let me just point a couple things out here. So this is how they have kind of worked this whole thing out here to find your delta S. You take the 2 moles times 192.5, which is the S for the entropy value for NH3. And then you subtract from that everything on the reactant side of the equation. Okay. Now notice the units for this, joules per mole times Kelvin. And then the moles are going to cancel out as you work this through, right? So then you end up with your entropy. The units for entropy are joules per Kelvin. Okay, so entropy is actually, turns out it's measured in an energy unit, all right? So that's useful because it means that we can deal with delta S and delta H kind of in the same equation sometimes because they have joules for their units. The delta S is negative here, and it's also, it's useful to kind of look at the original equation and see if that makes sense. Does it make sense that this is a negative entropy change? And why does it make sense? Okay, it's forming bonds. So what are we looking at here to say that there's less entropy on the product side? Yeah, so there's 4 molecules on the left side, right? Or 4 moles, however you want to say it. And there's 2 on the right. So we have decreased the number of molecules, so there's less possibility for where they can all be because now the NH3s are, they're attached to one another. Okay? So it makes sense that it's negative. Entropy change in surroundings. So this part of... Yes, that is part of it. This part, I don't think we need to worry about quite as much. I don't think there's going to be a calculation here. But, yeah, and I'm pretty sure, again, this equation, we've already seen this equation once, and it's not on the AP equation sheet, so I really don't think you're going to have to do an actual calculation with this. But you do need to think about this. Okay, so the universe is composed of system and surroundings. So delta S of the universe is the delta S of the system plus the delta S of the surroundings. And this is kind of what we talked about before. At best, at very best, you can keep the entropy from increasing at all. Okay, that's the best you can do for the universe. For the universe, delta S could equal 0 in a reversible reaction. Okay, so an equilibrium reaction, delta S is 0. In any other process that you do, you are going to increase the entropy of the universe. Okay? For spontaneous processes, the delta S of the universe is going to be greater than 0. That's what I just said. Where are we going with this? T delta S of the universe. Oh, okay. Yeah, that's where we're going with it. Not that this really matters, but this is how we kind of get to the idea of Gibbs free energy, which is what we're going to start talking about tomorrow. Which actually, maybe this... Where is that derivation? Yeah, that derivation is in the Gibbs free energy, so we'll talk about this next time. But basically, the ideas are pretty basic here. I don't think you're going to have too much trouble with this. There's a lot of practice that goes with it, and they tend to ask these kinds of questions on the AP exam. A lot of times what you'll get is they'll give you the delta H and the delta S, and then you'll have to predict is something going to happen spontaneously or not, and that gets into the delta G stuff we're going to talk about tomorrow. Okay? All right, that's it.